Welcome to qnawire.
Hi everyone, so what we have is a shower head that has a volume flow rate of water of 10 liters per minute. There is an electrical heater that is heating the incoming water, which comes in at 16 degrees Celsius to 43 degrees Celsius. And given that the density of water is 1 kilogram per liter, we are asked to find the electrical power required to heat this water up. Then, what we're also asked to do is find electrical power and cost saving for a 10-minute shower if we're actually exchanging heat with some of the water that's drained coming out at 39 degrees Celsius, and that heat exchanger has an efficiency of 0.5. So what we're going to do first is go through our assumptions. We're going to assume that everything's operating at steady state conditions, so the properties will not be changing with time. We're also going to assume that water is an incompressible substance, so there is going to be no changes in density. And we're also going to assume that any changes in potential energy, any changes in kinetic energy are also going to be negligible. So next we're going to write down the properties that are important to us. So we're given that the density of water is 1 kilogram per liter, and we also know the specific heat of water is going to be 4.18 kilojoules per kilogram degrees Celsius. So next we're going to do our energy balance. We're going to define the pipe as our system, and as we do our energy balance, we see that the total energy coming in minus the total energy leaving the system is equal to the change in energy of the system. Now, as we said before, we're operating at steady state, so the total change in energy of the system will be equal to 0. Therefore, energy coming in is equal to the energy leaving. Now we can break this apart into its constituents. We can say that this is going to be equal to the electrical work that's coming in plus the enthalpy coming in is going to be equal to the enthalpy leaving. Now we can isolate this work and say that work is equal to m dot h2 minus h1, and by using the definition of the pressure and temperatures, we can say that this is going to be equal to m dot C T2 minus T1 plus V P2 minus P1. However, this term will be equal to 0 because we're assuming we're operating at constant pressure. So this reduces down to m dot C T2 minus T1. And we can actually go ahead and solve for m dot just by using the volume flow rate and density. We can say that m dot is equal to rho V dot, and this gives us an m dot equal to 10 kg of water per minute. Now substituting this in back to our expression for work, we see that the total electric work required in the first scenario is 18.8 kilowatts. And that's the first part of our answer. Next, what we need to do is introduce this heat exchanger. So we need to determine what the energy that's recovered by the heat exchanger is. So by using the definition of efficiency, we can say that the total Q that's saved, the heat that's saved, is going to be equal to the efficiency times the maximum heat that can be saved. So by plugging this in, we can see that this will be eta times the mass times the specific heat multiplied by the difference in temperatures. So T max minus T min. And by plugging in for all these quantities, we see that the Q that's saved is 8.0 kilowatts. Therefore, we know that the new amount of electrical work in the new scenario when we're using the heat exchanger will be W new is equal to W old minus Q saved. So by plugging the W old and Q saved in, we see that the new electrical work required is 10.8 kilowatts. And that is another part of our answer. Lastly, we're asked to solve for the amount of money that is saved by using this new system. We know that each kilowatt hour is 11.5 cents. So what we can do is say that since we are saving 8 kilowatts, we can say 8 kilowatts times 10 over 60 hours times the rate, which is 11.5 cents per kilowatt hour, 11.5 cents per kilowatt hour, gives us a total savings of 15.3 cents over the course of a 10-minute shower. And that's our final answer.